Let's now take a look at how E values affects electrolysis. There are three forms of electrolysis. We can have electrolysis of molten ionic compound, which will be straightforward because if, for example, we were to electrolyze aluminum oxide or bauxite as is all, then we would actually get, then at the cathode, we will have Al3 plus reducing to aluminum and oxide oxidizing to oxygen at the anode. Next, we look at is the electrolysis of aqueous ionic compound. An example to look at now is dilute NaCl. If you look at dilute NaCl, in terms of at the cathode, we would have Na plus and H plus that's attracted to it. And also mindful, water, which is a polar covalent molecule, could also be attracted towards the cathode since the oxygen is delta minus. Given that these three are at the cathode, the question to ask now is that who should get reduced? So using the standard electrode potential value, we can say that if your standard electrode potential value is more positive, then you ought to be reduced at the cathode. Let's take a look at the standard electrode potential value in the data booklet, in this case specifically paragraph 4a. Since H plus, water and Na plus are going to be all at the cathode, which will undertake reduction, they should be right-hand species. So the first thing that I need to do is to underline all the species involved, and since all undertakes reduction, they all must be the left-hand species. So that is your H plus, which is 0 volt, your Na plus, which is negative 2.71 volt, and your water, which reduced to form hydrogen gas, and that is negative 0.83. So based on this, we are going to select the E value that is the most positive. So it certainly cannot be Na plus because the E value of Na plus is the most negative. Okay, and the next part is to rule out Na plus. The reason we rule out Na plus is because in this standard electrode potential value, we are assuming the concentration of H plus to be 1 mole per dm cube. But given that the electrolyte is aqueous sodium chloride, where the concentration of H plus is 10 to the power of minus 7 mole per dm cube at 298 Kelvin, since its pH is 7, we can conclude to say that the con H plus is way too low. So this value of 0 volt is not realistic, as if the concentration of H plus is extremely low, the position of equilibrium will shift backward. The value will be way more negative than the 0 volt that's displayed. Hence, because of this, the half equation that takes place is the one that is negative 0.83 volt. That's the equation, that's a half equation taking place at the cathode. Let's now take a look at the anode. Similarly, in the anode, there are three species. Certainly Cl minus and OH minus, which are both negatively charged. And water, as we explained earlier, water also have electron deficient or protonic hydrogen that could be attracted to the anode. Let's underline those species that can undertake oxidation. We'll be taking the 1.23 volt, the 4OH minus, which is 0.4 volts. And for Cl minus, we will pen them here for the ease of the discussion. And the value is 1.36 volt. So with these half equations that are all going to take place at the anode, we should be choosing the half equation which is the most negative. So in this case, it definitely cannot be Cl minus going to Cl2 since its value is the most positive. And next, it cannot be OH minus. The reason is again because in dilute sodium chloride solution, the pH of the solution is 7, which means concentration of OH minus is 10 to the power of minus 7 mole per dm cube, which is way lower than what it is displayed here, because based on standard electrode potential value, concentration of OH minus ought to be 1 mole per dm cube. So again, with OH minus being of a significantly lower value, the position of equilibrium will shift forward, therefore making this number way bigger than the 1.23. Therefore, the correct equations to pick is where water oxidizes to form oxygen. So this is the half equation that takes place at the anode. The final example we look at is the electrolysis of concentrated aqueous ionic compound. In this case, let's pick the example concentrated HCl-AQ. And for the case of the cathode, the H plus will actually be preferably discharged since it is the most positive, which is 0 volt. We will not pick this half equation since the standard electrode potential value is negative 0.83. As at the cathode, the half equations that is favored is the one that is more positive. And it is also important to add to say that we expect the concentration of H plus to be high since it is a concentrated HCl. However, at the anode, we still have the same three species. They are contending to actually to be oxidized. And it is important to note that OH minus will be immediately ruled out since the solution is acidic. Therefore, you'll be left with water, which is 1.23 volt, and your Cl minus, where the standard electrode potential is 1.36 volt. So therefore, H2O is going to compete with Cl minus to be preferably discharged at the anode. To do that, we need to bear in mind that it's concentrated Cl minus. Concentrated Cl minus means that the concentration of Cl minus is high, is extremely high. If the concentration is high, PoE will shift backward based on the Chatelier principle. So we expect the standard electrode potential value of 1.36 volt to drop below 1.23 volt. Hence, because of this, Cl minus is preferably discharged instead of oxidizing your water molecules to form oxygen. So let's now take a look at electroplating and anodizing of metal, and both of which are electrolysis. So first, we take a look at copper electroplating. In the case of copper electroplating, the electrolyte that we use is your aqueous copper 2 sulfate. So in this case, at the cathode, we will have Cu2 plus and your water. And the two half equations that we pick from the data booklet will be as such. So the two half equations that we're looking at is water. The other one is your Cu2 plus 2E to give you your copper. And that will be 0.34 volt. So the two half equations we're looking at is Cu2 plus and your water. So in this case, this Cu2 plus will be favored to be reduced since the standard electrode potential is 0.34 volt, which is more positive in value. Let's take a look now at the anode for electroplating. In the case of anode, you will have sulfate, water, and your copper. We'll first rule out sulfate. So in the case of sulfate, it's ruled out because its E value is highly positive relative to the other two. So in this case, sulfate going to peroxo disulfate will have a standard electrode potential value of 2.01 volt. While in the case of water oxidizing to oxygen will be 1.23, and copper going to copper 2 plus to be 0.34. For the reactions at the anode, as since all the species are right-hand species, we'll be picking the standard electrode potential value that is the most negative. In this case, the most negative reaction occurs when copper oxidizes to form Cu2 plus. That's the reason why this is the half equations that take place at the anode. Which means, in a nutshell, the copper competes effectively with the anion that's attracted to the anode. That means copper competes effectively with the anions that are attracted to the anode to be oxidized. And in copper electroplating, it means that in copper electroplating, the object to be electroplated should be placed at the cathode, while the copper source or the impure copper source will be placed at the anode. In the case of electrolytic refining, is the purification of metal. To purify the metal, in the same vein, the impure metal is at the anode, while the pure metal is at the cathode. Since at the cathode, Ag+, which has a standard electrode potential value of 0.80 volt, is highly positive, and it will be preferably reduced at the cathode. While at the anode, nitrate has reached its maximum oxidation state of +5, and if you look at the data booklet, nitrate species are on the left-hand side, which means it can only be reduced and cannot be oxidized. Therefore, it will not be discharged at the anode, leaving silver and water to compete to be preferably discharged. In this case, silver will be preferably oxidized since it has a less positive standard electrode potential value. Finally, in the case of anodizing of aluminium, the purpose is to allow aluminium to be coated with a uniform, homogeneous protective layer of impermeable and inert aluminium oxide. The way to achieve that is to make aluminium the anode. And at the anode, the half reactions that need to take place is where oxygen is being produced, and that can be produced by oxidizing OH minus or oxidizing water. And the oxygen that is produced could then chemically react with the aluminium to form a uniform impermeable inert aluminum oxide layer. Finally, to put everything in context, the first step to do when you see a question that's related to electrolysis is to check whether there is a battery. If there is a battery, then it will be an electrolytic cell. Whether is it electrolysis, electroplating, or electrolytic refining or anodizing of aluminium, which we have covered, the battery must provide the external current. However, in the case of an electrochemical or electric cell, it itself is the battery. So in this example that we have electrolyte as being your copper 2 sulfate. So the anode is the one that oxidizes, which means the more reactive metal, zinc will oxidize in this case. Or otherwise, what we could deem is that we can see that the water, OH minus, and sulfate are at the anode, and the species with the most negative standard electrode potential value would oxidize. So in the case of water, it is 1.23 volt from the standard from the data booklet. For OH minus is 0.4 volt. For sulfate is 2.01 volt, and zinc clearly is the one that will preferably discharge, since it has a standard electrode potential value of negative 0.76 volt. And that explains why zinc readily oxidizes. While at the cathode, the same analysis will be utilized. In the case of copper, the standard electrode potential value is 0.34 volt, while in the case of water reducing to form hydrogen gas is 0.83 volt. So therefore, because of that, Cu2 plus will be reduced to form copper.